Good morning, everyone, and welcome to Physics A. Today I want to discuss full projectile problems. And they're a little different than the half projectile or cliff type because we have an object that leaves the ground and then goes up in the air and stops and then comes back down. So I want to introduce the math today. So there's going to be quite a bit of math in this video. Please take your time, watch it a couple times, and so the notes will be provided, of course, in the class as well. So here we go. We have a projectile shot from a cannon, and what we've done is we have a lower angle. We're going to make this angle to be about 35 degrees. Okay, and as you notice, the object goes to a certain height and stops and comes back down, and it is shot to a specific distance or range. Okay, this is the range. But what we want to understand is that if I change the angle of the cannon to shoot up higher, that projectile will go in the air higher. It will still go to the top of the path and stop and then come back down. But its range will be much shorter, but its time in the air will be much greater and the height that it reaches. So there's a different purpose for doing these things. Maybe you want to fire at something or you want to hit something farther away. Okay, maybe you just need to clear a path. We have to go over something like trees or whatever to get back down. So even a golfer does this. A golfer may hit a ball in an arc like this that maybe needs to go farther, but maybe they have an obstacle they need to go over to get to their hole. So anyway, the idea is when you change in a full projectile, the angle that it's fired from, you get different answers for different things. So I want to show you how to break down a full projectile problem, okay? When you're doing a full projectile problem, the given velocity, so I'm making this cannonball come out at 60 meters per second in both cases. It's the exact same speed from the cannon, but what I want you to understand is that when it's shot, it is not the original speed that's important. It is actually the speed that it moves both vertically and horizontally that are more important. And so we have to learn how to break those down into these two pieces, and this is what we're talking about when we come to trig. The horizontal piece, since the side is adjacent to the angle, uses cosine. So the cosine of 60 degrees equals adjacent, which is my unknown height, horizontal piece, over the hypotenuse, which is the given number. And if I solve that one and I multiply the 60 up, so all we have to do is bring the 60 up over here, and we find out that our cosine of 35 times 60 equals 49.1. And that's going to be meters per second, because remember, same unit. If I want to find the vertical piece, it is opposite. The function of sine has opposite and hypotenuse. So all we always use here is the function of sine. So the function of 35 degrees equals x, which is now the vertical answer, over 60. We bring the 60 out front again. And so we just take our formula. We go sine of 35 times 60, and we find the vertical piece is 34.4 meters per second. So what we're finding out is that in this low range or lower angle, we have greater speed horizontally that the object comes out. But remember, the horizontal piece never changes. So everywhere in this path, the speed horizontally is identical. Okay? But upward, okay, there is only 34. It comes out vertically at 34 meters per second, and as it goes, it begins to lose that speed more and more and more till it actually stops going upward at any speed whatsoever, and then turns around, okay, and then returns again to the 34. So it is more moving horizontally than it is vertically. If I change it to the complement, a complement of 35 means 35 and 55 add to 90. If I change it to the complement, what happens, I bring this line down, I get my 90 degrees I did here, okay? I now have my vertical and horizontal components. I do the exact same math, except I change the angle. So the cosine of 55 degrees equals x over 60. Bring my 60 out front. And the sine of 55 degrees equals x over 60. And I bring my 60 out front. So all I have to do is change this, but what I find out is we go the sine of 55 times 60 equals 49.1. So what happens is these two triangles swap their horizontal and verticals. And so what happens is now there's more speed going up from this cannon. And what's happening is it begins to slow down, okay, and then stop. So, but it's going up at 49.1 meters per second. But the horizontal is now smaller, but still consistent as it moves through its path, okay? But horizontally, it's still moving here. I want you to remember that. It's always still more, but it's not as great as it was there because of the lower angle. So what's happened is now the object is moving up faster, more vertically than it is horizontally. And that's the reason why it doesn't go as far. So this is the first thing you must do every single time on these problems is you need to break the original speed into its two pieces based on the angle of the projectile. And that is important, but all you're always going to use is cosine and sine. Cosine will get you the horizontal and sine will get you the vertical. It's the same process every time. That's the first thing we need to do. Then we can actually analyze all of the motion. So let's look at time, horizontal speed, which is constant, and the vertical speed, okay? And what happens? Well, when it's at 0, okay, it originally starts horizontally, coming out of the gun, moving at a speed of 49.1. So I'm not going to consider this synopsis. So we can't do both. So I'm just going to look at one of these scenarios. So we're going to ignore this scenario for right now, okay? So let's look at this one. It comes out at 49 horizontally. So when time is 0, there is some speed. It is 49.1 meters per second. And as time goes on, the speed never changes. So every second of time, it stays at 49.1. 49.1. And that goes all the way down. So there is 0 acceleration. Okay? However, vertically, because we have gravity pulling on it, there is a decrease in speed till we hit 0 and then an increase in speed. So let's analyze the vertical component. There is acceleration going on. And so because of that acceleration, we know that there's going to be some changes. It first comes out of the gun vertically at 34.4 meters per second. But it's undergoing acceleration. At first, it's deceleration, then acceleration, but changes downward. So remember, we always are using it as negative 9.81 meters per second squared. And so all I got to do is subtract that number. So 34.4 minus 9.81 is 24.59 or 24.6 meters per second. Then after 2 seconds, I subtract 9.81 again, and I get 14.8. Then I subtract 9.81 again. After the third second, I get 5.0 meters per second. And then I subtract it again. Of course, but we're going vertically, so these are all positive. Okay. Then I subtract again 9.81, and I get negative 4.8 meters per second squared. Then I negative again, I'm minus 9.81, I get negative 14.6 meters per second. But what's happening is I have slowed down. Somewhere in here, we've passed the middle point. So now we've turned around and started coming back down. So now my velocities have changed from a positive speed to a negative speed, because remember, down is negative and up is positive. Okay? Very important. So that's what's happening here. And once I reach Any number greater than 34.4, we know the object has landed and has stopped, okay? So that's how you analyze the speeds on a full projectile problem. It's not difficult. You just do subtraction here. Here it's the same number because there is no acceleration. You just have to have broken down with trigonometry the original vertical and horizontal speeds of the original speed before you begin. Okay? Well, with that in mind, we can actually go and then begin to analyze the heights and the time in the air. So let's do that. Okay? So I'm going to turn this over here. We're going to use the same information right here as what we started with, and we're still going to analyze only the situation of where we're shooting at 35 degrees. Okay? So how would we do that? How would we find these pieces of information like average speed or final velocity, initial velocity? Well, it's pretty simple. We can fill in quite a bit of this chart really easily because horizontally we talked about it going at constant speed. That constant speed means there is no acceleration. So that's simple, okay? But we also know that the original speed going this direction to the right, horizontally, we started off an original speed of 49.1. And we also know at the end of the path, it's still 49.1. And so the average of that is 49.1. Okay? So actually, they're all the same number. Pretty easy. Well, but this is called the range. And we can try to figure out how far it went, but we can't do that until we've analyzed all of the vertical part. So this range answer in this time in the air, okay, in the time in the air, they depend on this information. So these two depend on vertical answers. And so I need to finish this list over here first before I can go on. Okay? So let's do that. We'll move this up here. We have our numbers here we're working with, and we got to have our vertical, and okay? So we know that vertically, okay, we are starting off at going 34 upward. So we started off at upward speed of 34 in this scenario at 35. So remember, this is at 35 degrees. 35 degrees and 60 meters per second. And 60 meters per second. Okay? So we started off vertically, initially going up right here at 34.4. Okay, our acceleration rate, as per usual, gravity's pulling it down, okay, and slowing it down, negative 9.81 meters per second squared. Okay, if I want to find here, this one will not be the range. This, since I'm dealing vertically, will be the maximum height that it reaches. Okay, so this distance and this distance, this is a horizontal one and this is a vertical one. Okay, on positive physics, this will be a delta x because it's horizontal. This will be a delta y. I just want to point that out. Okay, and so going on from there, let's try to figure these out. What equations can I give you? I'm going to give you the equations that you can do to solve the rest of this chart. It's really simple. If we can have one more piece of information, then this is going to be easy to solve. That piece of information is at the top of the path, it hits 0. So I'm going to analyze only half of this path. At the top, it is 0. So I'm going to put a 0 here for its final speed for half of the overall flight. Okay? Half the flight. Well, then what that means is to find the average in this half a speed, okay, is going to be the adding these two together, because average is adding to, so it's VF plus V0 divided by 2. This part is 0, okay, so I just basically divide this number by 2. So 34.4 divided by 2 is 17.2 meters per second. So that's really a simple problem. Okay, this one is given to me. This one was given to me from my original trig. And this one's always given to me because when anything is affected by gravity, which is projectiles, in the vertical direction, it's always negative 9.81. So then how do I find these? Well, the best way to find these is to find an equation. I don't have any t, so what equation has distance in it but no time? It is VF squared equals V0 squared plus 2AD. And if you think about this one, this VF is 0, so you square the V0, you bring it to the other side, it makes it negative, then you divide by 2 and A. So we're going to do that. My formula, V0 squared, I'm going to square this one, so 34.4 times 34.4 equals this number, it's squared, okay? And then I'm going to divide it by, because it's bringing it to the other side, so I get a negative V0 squared divided by 2A, and this negative V0, which should be negative, is also going to be divided by a negative 9.8, so they're going to cancel out. And so I'm going to get a positive distance, which is correct because I'm going upward. It's positive. So let's do this. So I'm going to divide this by 9.81 equals, and then again divided by 2 equals, and I get 60.3. And that's how high this object will get right here, 60.3. Okay? But I want to find time in the air. So let's find an equation with time in the air that doesn't have distance. And so we can do that one. And so I'm going to use A, the equation, A equals VF minus V0 over T. Okay? I'm going to switch these two letters around so I get T equals VF minus V0 over A. Remember, VF was 0, so I get a negative V0, okay, which is negative 34.4 divided by negative 9.8. So I get a time. So let's do that. 34.4 divided by 9.81, and I get an answer of 3.5 seconds. So time is 3.5 seconds. Okay, so now I've just found the time, but I got to be careful. This is only time for half the path. So if that's correct, then that means to have the full flight, this is half the flight. If I want to know the full flight time, we call that sometimes flight time, I would just simply multiply this number by 2. So this is T times 2. So 3.5 times 2 is 7.01 or 7.01 seconds. So that's really what I want to put in there, okay? And then why it's going up and down over here, it's moving all the time horizontally. So now I can go back to this information and solve for it, but since it's constant, we can only use this equation, okay? Or we may know it as delta x over t, okay? So I want to solve for, I'm going to use this t, so I can just transfer this information over. Time in the air came from 7.01 seconds, okay? And that's because it depended on the vertical answers. Now to find range, I simply get x by itself. So I just multiply the t up. So the range, or d, equals v horizontally times time. So I don't use the vertical speed. I use the horizontal speed, okay? Because that's what it's going. So it's really 49.1 times the 7. 49.1 times the 7.01 seconds. And that gives me a distance of 344.2 meters. So now I actually have the distance and the time, but I had to solve this information first over here. So now you have the equations that you need to use for each scenario, and you might want to put them on your own sheet of paper And then that way you have them available, okay? And so these are the equations for those. These are just part of our given list and can be found really pretty simply, okay? So that helps you fill in a chart with all these values here from an object undergoing a full projectile, okay? So watch that again, follow the math if you need more help, and so go ahead and keep doing this, but that's how you would fill in these kind of charts from a velocity or a velocity chime chart changes, or trying to find time in the air and maximum height or range of that projectile. Okay? There you go. God bless.